An introduction to capacitive level sensing. To explain capacitive level sensing, we must first understand the concept of a capacitor. A capacitor is formed by two electrodes, electrically insulated from each other. The electrodes themselves must be conductive and are typically made from metal. They can be any shape, though two parallel plates are easiest to visualize. Capacitors have the ability to store energy in an electric field between its electrodes, caused when a voltage, or potential, is applied to the circuit. The property of capacitance relates the amount of energy stored in this field to the applied potential. By placing non-conductive material between the electrodes, the ability for the capacitor to store energy increases, and so the capacitance increases. This material between the electrodes is referred to as the dielectric. The key property of dielectric materials is known variously as dielectric constant or relative permittivity. This property is the amount of charge the material can store, defined relative to a vacuum. Air and other gases, such as fuel vapors, have values very similar to a vacuum. As a dielectric liquid is introduced between the electrodes of the capacitor, the capacitance changes progressively and liquid level can be determined. To measure variations in capacitance, electric energy flowing into and out of the electrodes is measured as the circuit potential is varied. A regular flow of energy is established by connecting the electrodes to an alternating current measurement circuit. The more energy flow to the electrodes, the greater the capacitance, meaning more dielectric between the electrodes. For sensor calibration, reference measurements at empty and full tank conditions must be taken. Generally, we need to know the dielectric constant of the liquid being measured to calibrate the sensor at its full condition. With the empty and full outputs established, liquid level sensing comes down to relating sensor output to these values. Capacitor plates can also be deployed as concentric tubes, with the advantage of reduced interference, as well as improvements in mechanical stiffness and robustness. Fully integrated electronics mean no external electronic units are required, as all signal processing is managed on board. Dielectric fluctuation caused by temperature variation is managed using offset values also stored within the sensor memory. These values are typically applied during factory calibration at GIL sensors. A wide range of fluids can be measured using a GIL liquid level sensor, including fuels, biofuels, diesel, and oil. And by modifying internal components, the liquid level of electrically conductive substances, such as water, can be measured. Sensors are often constructed from aluminium, stainless steel, carbon fiber, or PEEK, or a combination thereof. This allows GIL to cater for applications from fuel tanks in Formula One race cars to oil transmission systems in mining and industrial machinery. Issues such as tank sloshing can be effectively managed using software or modifying the fluid dynamic damping features within the sensor construction itself. GIL liquid level sensors are highly accurate across a wide operating temperature range and offer unmatched long-term reliability in harsh and unforgiving environments.